So this is our problem statement. The solver that we'll be using is buoyant pimple foam, simulate the natural convection, and as ma'am specified, we'll be selecting certain boundary conditions for this buoyancy-driven flow. So what is our problem statement? We again have a rectangular geometry. We have one bottom face. The left face is our flat plate. Then we have a curved face and the right face. Okay. So all of those faces, like bottom, right, and top, are at 300 Kelvin, and the flat plate is at 350 Kelvin. So we are giving a 50 Kelvin difference. Now we have to choose a boundary condition appropriately. Now what we want to do over here is we want to mimic this profile that we are getting. This is a snapshot from Infrared. So here we should get a temperature at the wall that is high and it decreases inside the thermal boundary layer, uh, and a velocity which will be zero at the wall. It will be maximum at the center and again starts to decrease till the edge of the boundary layer. This is what we should get. Our dimensions are, the box dimension is, the bottom size is 10 centimeter and the height is 60 centimeter. Okay. So now I will open so I've extracted those data over here. So you have to extract this file, natural convection vertical plate. So when you extract that, you will get this. So it will be in two folders. So as yesterday, even Harish pointed it out, because it is zipped, it opens in two folders. You open the first one, open the second. Inside this, when you have zero constant system, copy that folder. Copy that folder to your run directory. Now to copy it, I have copied it. Now to go to my run directory, I am going to Ubuntu over here on the left. I'm clicking over there. My run directory is in the home. Go to home, my user, open form, and run. So inside this, I will paste it. Okay. Now I already have. So I create one new folder for time being. You don't need to create that. Just paste the folder over there. Open your Ubuntu terminal. Has everyone done that?
So can you explain again how the copy and paste in which
Yes.
directory?
Yes. So you have downloaded this, right? So it will be downloaded in some directory. I have downloaded it on the desktop and I have extracted it. Okay, it might be in the downloads directory for you. Go over there and extract it. When you open, there are a lot of files because we are doing 2-3 cases, right? So I have given everything. Now you have to extract the natural convection vertical plate case. So you extract it. This folder will come. Inside this, there is another folder. So you copy this folder, natural convection vertical plate. Have you done till there?
Yes, sir.
So when you copy it, you have to paste it in your run directory, right? So now I'm showing you how to browse the run directory in your Linux, right? So in your file browser, in the left-hand side, there will be Linux over here, right? Inside that, there will be your Ubuntu version in which you have installed OpenFOAM. Click on that. The file structure inside Ubuntu will open up. You click on Home. Inside Home, your username, whatever is your username, that will show up. Open that. Then open the OpenFOAM directory. Inside OpenFOAM, again your username. Then inside that, run directory will be there. There you paste that. Okay, in your run directory. Once you paste
Okay.
it over, once you paste it over there, then you will be ready. Ready. You can run the simulation now.
Okay. Thank you, sir.
Yeah. Okay. So has everyone done that? There is no run in my name folder. Okay.
Uh,
Swapna, you might have installed in some other directory. So this step that I told you, right? Where is your run directory? Hmm? Okay. If you are not able to find run directory, do one thing. I'll give you another hint. So once you open your terminal, type run, run, and then type explorer.exe and then dot. So directly wherever is your run directory, it will open that location. So see, it opened, and the path for me is whatever I told you, right? In Ubuntu, home, and then my username, then OpenFOAM username, and then run. So if you're unable to find your run directory, do this step. Okay. Open your Ubuntu terminal, type run, and then type explorer.exe space and then dot. That will open your run folder in your file browser. You should be able to paste it. Just see if you have copied it properly and paste it again. If not, try to do that. If you are still having some problem, then there may be some glitch.
Asking for some administrator privileges.
Okay, then what you can do is try with the cp command, cp minus r. Are you not able to paste it anywhere? Can you paste it in the home? Okay. Have you installed, is your OpenFOAM installation in root by any chance, or is this the
No, no,
same
no.
location?
It's
No.
okay.
Excuse me, John.
Yes.
After opening the explorer.exe and where I can copy paste this file.
In your run folder.
Okay.
Your run folder, right? Paste it in the run folder. So when you paste it in the run folder, you should be able to see your natural convection vertical plate. So for me, it is available over here. Natural convection vertical plate. After that, you can open that folder by typing cd and then natural convection vertical plate. Okay. I just press tab, it will complete it for you. Now inside this, we have a zero, constant, and system folder. Okay. Let me go and see what are the contents of zero folder. So in zero, right now I have PU, PN, PRGH. So we need to give boundary condition for all. So we'll just quickly go and see what are the boundary conditions. So let's start with, say, PRGH. I'll open it with Notepad. Now here, if you look at the PPT over here, we have told you what are the appropriate boundary conditions, right? So for PRGH, at the bottom, the appropriate boundary condition is the total pressure. As ma'am said, in such cases, at the inlet, you should specify the total pressure where the flow starts. So there we are specifying total pressure of 1E5. That is what we have done over here. We have specified a total pressure, PRGH total pressure of 1E5. And at rest of the places, so okay, this is one more trick. So whenever you see something written this way inside quotes, instead of writing the same boundary condition for all the files separately, we can write it together. Not all the files, all the patches separately, we can write it together by using this quotes. So that means whatever is this boundary condition, right, specified over here, it will apply it to both, to all top, right, and flat plate. So this will save you from writing multiple things. Okay, and so what we are specifying, PRGH total pressure at the bottom, and at the top right and the flat plate, we are specifying fixed flux pressure. So it will calculate pressure from the, what you can say, flux, right? What ma'am explained to you. And front and back, we are not solving, so that is empty. So this is the content for your PRGH file. Initially, we are giving uniform inlet field, right? PRGH value of 1E5. So to open the U file, you have to type notepad.exe and then U. Now, in this, we are specifying an initial velocity, that is the internal field initially is 0 throughout. The x, y, z component is 0 throughout. Then at the bottom, we are specifying something called as pressure inlet outlet velocity. That means it will compute the velocity from the pressure. And this value is just a placeholder for the initial guess, something like that. Right? At the top, we are giving an inlet outlet boundary condition. That means it will allow for, if there is a possibility of any what we can say reverse flow, it will allow that. But we are specifying that the reverse flow velocity should be 0. Now these are the boundary conditions which we have found to be stable. The others are not working. So these they do work. Now at the right, we are giving a 0 gradient. That means it will compute from the internal cells. At the flat plate, it is no slip. No slip means 0 velocity at the flat plate. Then front and back as before, it will be empty because we are not solving in that direction. These boundary conditions also you can find over here. They are there in the, over here we have mentioned. So we have looked at the U boundary conditions, the PRGH boundary conditions, and lastly the temperature boundary condition. So to look at the temperature boundary condition, just do notepad.exe and T. Now for T, initially throughout the temperature is 300. At the bottom, again, we are saying that whatever is the flow that is coming in should have a temperature of 300. Okay. At the flat plate, we are giving a fixed value of 350. And top and right, we are giving zero gradient. That means it will compute the temperature from the internal cells. And the front and back is empty. So this is your boundary condition for temperature. Now after this, I think boundary, that's it, the boundary conditions. Now next, let us look at what is the, okay. So I have looked at the zero folder. Now let us look at the constant folder. Now in constant, we have momentum transport, G, and thermophysical properties. So if I will open G file, type notepad.exe and then G. So if you see over here, G value is specified. So our G is in the negative Y direction. If you look at this setup, we are pointing in the, no, don't look at this. So our X is in the, what you can say, along the bottom wall, and Y is along the flat plate. So since it is vertical, our G will be downwards. So we have to specify G in the negative Y direction. So that's why G value we have written as in the second this value over here, not in the first. So G is in the negative Y direction, and that is 9.81 meter per second square. So we need to specify G for this because gravity is what is driving the flow because of density difference.
Excuse me, sir.
Yes.
Sir, can you please open the T property file again? I have to ask a question there.
Yes. Yeah.
Yes, sir. Sir, in this, the boundary field for the bottom part,
Yeah.
we have given the inlet value of uniform 300.
Yes.
Then why we have again given the value uniform 300 in the next?
That is just a syntax. It needs some what you can say placeholder. Okay, that is the syntax structure for the inlet outlet boundary condition. Like over here, see, where was the other case? For some case, right, where value was not needed. I told you value is just a placeholder. So this is the structure that OpenFOAM has. So whatever is the value for inlet is 300. And if there is any outflow, it will be by the zero gradient.
Okay, sir.
So that does not get calculated.
Okay, sir. Thank you.
Okay. Okay, I showed you the G file. Now let me go and show you what else is there. So along with G file, we have something called as momentum transport. So in momentum transport, we have made the simulation as laminar. We are not running a turbulent simulation as of now. You all can explore that. So in momentum transport, to make the simulation as laminar, you have to just name the simulation type as laminar. So if you name it as laminar, whatever is mentioned below that, it will not take, even if it is mentioned. If you remove this also, it's fine. Just write it as laminar. Next is the thermophysical properties. Now this is something that is interesting. Yes. So where are we going to specify the Boussinesq approximation, right? So Boussinesq approximation will be specified here. So here you have to specify what is your what you can say, what is your working fluid. So our working fluid, we are saying it is a pure substance, pure mixture with constant transport properties. Okay. And the equation of state that we'll be using is Boussinesq approximation, and we will be solving for the internal energy. So that's why E constant. E is the internal energy, sensible internal energy, right? Now, what are the what are the properties of this? You'll specify in the mixture over here. So the molecular weight, this is air, so molecular weight is given as 28.9. Then this is important, right? Because for booziness, ma'am said you need to give a reference density, a reference temperature, and a thermal expansion coefficient. So my rho zero is my reference density at temperature T0. This is my reference temperature. And beta, that is the thermal expansion coefficient, is 3e minus 3. That is, this you calculate as 1 upon T generally for ideal gas assumption, right? Beta is approximately equal to 1 by T. This you can calculate. Then some thermodynamics properties are needed. CV, specific heated constant volume. It may not use this for calculation, but see, it will not use this for calculation. It may not use this. It may use some part of it, but all of this have to be specified. If you don't specify, then it will not work. It will give you an error that say transport model is not specified or species is not specified. Such errors it may give. So that's why you need to have all these values. Now, transport properties, as you know, viscosity and Prandtl number is given. So you have to specify over here. And if you have to change any of these values, then you know that you have to change it in the thermophysical properties. So these are the two files. Now, once we do that, one more thing. So we have finished the zero constant, and now we have to go to the system folder. So I'm doing CD system. So in the system folder, we have block mesh dict. So block mesh dict is already edited. It is just simple, like a cavity case. I'll just maybe quickly show you that we can run. It is like the cavity case. Here I've written convert to meters at 0.01 so that I can specify these values in centimeters. So my x is 10 centimeters and y is 60 centimeters. And I have given some grading. So this you can give, sir was talking about grading, right? So if I give this grading in the x direction, that means my cells near the wall will be finer and away from the wall will be coarser because I want to capture the boundary layer near the wall. That's why I'm giving a grading in the x direction. Once I run the block mesh command, I will show you this. But I think this sir has also showed to you. Now the different boundary patches are bottom wall, bottom, top, front, and left and right. These are my patches. Now next, okay, I have also included something called as decomposed power dict. If the runtime is more, if you want to simulate for a longer time, then you can decompose it. One more important thing is that I have added something called as FP constraints. Okay. This will come in handy for you. This will come in handy for you when your simulation diverges. So this is one trick. What you can do is, in certain cases, if your code is saying that you are getting negative temperatures, it is not able to do that. The first thing is to fix your boundary conditions. Then what you can do is you can add this constraint. So what constraint I'm adding? I'm limiting the temperature in all of the region to between 300 to 350. This is physical because your lowest temperature in the domain is 300, your highest temperature in the domain is 350. You cannot have a temperature higher than this or lower than this. So while calculating, suppose if your solver does not, what you can say, predicts an incorrect temperature, it will not allow it to go beyond this range. So this FP constraint is very helpful if your solution is diverging. So this we have added. Rest of the files are same, so you don't need to do that. Maybe if you want, you can look at the FE schemes and FE solution as to what schemes have been used and what solution has been used, like Gauss linear and all those things. Now to quickly run the simulation, I am in the system folder, so I need to be in my main folder. So I'm doing cd dot dot. If I'm in this folder, I need to run block mesh. First command is block mesh. As soon as I run block mesh, so you see my meshing is done. I can view the result by typing parafoam. Let me do touch result of foam and open. This I'm doing only to show you the mesh. You don't need to do this. Okay. So if you see, I am making my surface to surface with edges. If you see, my mesh is finer near the wall and coarser away from the wall where I don't need it. So this is the effect of grading, because I've said that my first cell should be 1/5 of my last cell, because I've given a what you can say a ratio as 5. That means my last cell is 5 times the first cell. So it will calculate that way. So if you look at this, I have a fine mesh near the wall and coarser mesh away. This is the effect of grading. So now once I have done block mesh, I need to run the solver. So the solver is buoyant simple foam. So the command is buoyant pimple foam. So make sure you type it correctly, the spelling. Viraj has typed it in the chat already. So buoyant pimple foam. Once you run that, your simulation will start to run. It will
Excuse me,
take
sir.
some time. Yes.
Where is this band pimple foam solver located?
All these solvers are available in your solvers directory, right? In your run, as soon as you type sol, you will get this. So this will be in your under your heat transfer section.
Okay, so if I want to add a equation, like let's say if I have to add a term in the momentum equation, let's say
Okay.
it's having a some different kind of like del T by del X something term. So
Yeah.
can I add it there?
Yeah, you can add it, but you have to be careful when you're adding. You have to see where where else it is getting used, and you have to be. You can add it over there. You can copy that. Don't add. So
Let's
adding
say
a scalar is
mm,
pretty simple, right?
no, no,
So
no.
you copy
I'm
that.
not asking to add like different equation, but I want
Mm.
to add a single term. So which ensures
Yes.
like some having a higher order term, let's say del power 4 kind of thing. So I
Yes.
need to add that term. So where can I add it?
You'll have to add it in your solver. You have to see how it is implemented first. Every solver is implemented differently. Okay, so the implementation will be much complex for those solvers. You have to see how it is being implemented, what you want to add.
Okay.
Okay, and while adding, you also have to see, make sure that your dimensions of your various equations are correct. Like you
Yeah.
cannot just, like suppose in my equation, I cannot just add +1 or +2.
Yeah.
If my source is there, I'm just giving an example, right? If some source is there, like in my present case, the Laplacian case, where was it? Yes, here. So if you see this equation over here, your
So
ddt.
let me add here instead of having so if I have a term like plus beta in del cube t per del x cube, let's say.
Yes.
So I want to add that term. That's it.
Yes.
So that is like these having a Laplacian and DDT only. DDT is kind of a represent del t by del t, and Laplacian for del square upon del x square, right? So if I
Yeah.
have to add del 3 power del x cube, let's say,
Mm.
so that term how can I add it there?
That you have to figure out. But one advice that I can give you is your say this. You see my first term, right?
Yeah.
Its unit will be Kelvin per second.
Yeah, that I understand.
This unit is Kelvin per second. This is also, that's why this also has to be in Kelvin per second.
Yeah,
So when
yeah.
you're adding, that has to be there. Okay. Because even in our case, we have tried to remove this source, and instead of adding by FB models, add a source ourselves, by defining some parameter. Maybe you
Okay.
want some constant to be defined. You can define that constant, and that constant can be taken from your uh, thermophysical properties file. You can look up. There is a lookup function which will be there in your. So you can't just change it over here. You also have to change the create fields dictionary and all those things. Okay. So it is not a very straightforward process. So you'll have to try, okay, and see where you're getting error and then change accordingly. So the run is over. So again, I will type the touch result.foam. Explorer.exe also you have to type, but for me it is open. After touch result.foam, please type explorer.exe. Okay. So you see my simulation is run and I have all these files. Then I can open the result. Click on apply. I have to look at U or my T. Let's look at T first, temperature field. So temperature at the last instance is this. So you see a thermal boundary layer forming over here, right, along the plate. Similarly, now if you want to see the velocity boundary layer, I am changing it to U. There is a velocity boundary layer. Now this profile that you are getting, where is it here? So see here, you see a temperature that is decreasing from the wall till the boundary layer, and for velocity it is increasing midway and then dropping. If you want to plot that, you can do something called as plot over line. Like this we have showed you already. So you have to plot, but this is along your x-axis. So you have to plot along your x-axis and then apply. Now scroll down, because it is showing you many things you are unable to see over here. So uncheck things like P, uncheck PRGH, and say uncheck U magnitude. So this is your variation of T. So T at the wall is 350, and it is decreasing as we are moving away from the wall. So this is similar to what we have over here, T at the wall, and it decreases. Now let's look at U. I'll uncheck T and look at U. So U from the wall, it increases, reaches one maximum, and then again starts to decrease. So qualitatively, we are getting the same result. Okay. Now, what you can do is, in your D3, there is one more case, that is natural convection in a cavity. For that, we have a video. This is around 12-minute video. You can watch this video. So in that, all the explanation about setting up the Business approximation, everything is given. Just watch this video and you can have this for your reference as well. So 12-minute video. Once you have finished that, you'll get an understanding of how that case is set up. You just have to run the case that is available in the cavity convection.
Hello, Zon, can you please again repeat the paraview part that you have shown for the previous lesson?
Okay. Once you do this, right, touch result.foam, you need to open the
Hello,
browser.
if I am using directly paraview,
No,
directly I
then
will write parafoam.
this is touch result.foam is only for people for whom the paraview is installed on Windows and you're opening through Windows. Yes. If you are using Linux or if your Ubuntu paraview is working fine, then you just type parafoam.
Right,
and it will open directly.
Right.
Okay. Now once you open this, you have to click on apply. Then you can view the say temperature profile by clicking on T and going to the last time step, last frame. So this is how the thermal boundary layer will form. Now, if you want to see how the thermal boundary layer is varying along, like in the direction normal to your wall, then you have to click on this plot over line function. So this plot over line gives you the ability to see the variation. Now, see, by default, it is taking 1 point over here at the bottom most and the other in that opposite corner. That is how it takes by default. So you'll have to first change it. You want to plot along the x-axis, so click on x-axis and then click apply. Once you do that, you see there are many variables that have been plotted onto the same graph. So if you want to plot only T, come to the properties tab. In this, you scroll down, uncheck PRGH, uncheck U. So this is only your T. Okay, this is how your temperature will vary. Now, if you want to see how your velocity will vary, you can uncheck T and check only on U magnitude. So your U magnitude will be 0 at the wall, it will increase and then again start to decrease. So this is what you should expect.
Sir, can we save that picture?
Thank you.
Yeah, you can save the picture. When you have that picture, anytime if you want to save, you have to click on File, Save Screenshot, or Save Data. When you do Save Screenshot, it will save the image. When you do Save Data, it will save whatever is that graph data in the CSV format. Okay, that means it will give you the value for every coordinate, XY coordinate. That is for every cell. I think that we have already demonstrated to you. It will be similar thing. There is no change in that process.
Okay, thank you.
Okay, welcome. So now you all can go ahead and watch that video, because that video will again take you around 12 minutes to watch, and maybe you can simultaneously do it also. If somebody is having a problem, then I will demonstrate.
Excuse me, John.
Yes.
You said that discretization process, DDT, like where
Yeah.
we write our equation.
Uh.
So can we see the discretization that is used for this equations?
Yeah.
Like
So
I want to see the discretized equations. Where can I see?
you want to know how it is discretized.
Yes, yes.
Uh, we mentioned terms like DDT, what to do, like Euler, right?
Yeah,
So
yeah.
it will discretize by Euler technique. But
So
how it is done
so can we see that like how it is
for
discretized?
formulation of Euler,
Yeah,
just
yeah.
let me check. You just watch the video. I'll just see in the source code once.
Okay.
Yeah. So if you want to share search anything, I
Okay.
will maybe show you all how to do that. So this
Okay.
will be helpful.
Okay.
So first thing what you do is go and type maybe open form. Now in this case I am typing 9, whatever it is. Now we are using the dot org version, right? Dot org.
Okay.
So you open this first link, openform.org, right? So this window will open up, right? This is their website. So you can go to resources.
Okay.
And then you can go to the C++ source guide.
Okay.
So here you will get all the source code. Now, depending upon version, the source code has changed. So you select the first appropriate version in which you are working. So now I'm working in 9, so I'm selecting 9. And then I can type this in the search. I can type some keyword, like say you want to know framework for Euler. So once I search that, okay, then what like how it is related, where it is solving, it will give some details about that, some small description of what it is. And if you want the source file, it is written over here, .c.h. When you click on that, it will give you the source code. This source code is available. See, this is the location in your SRC, that is source code, ODE solvers, Euler, and Euler.c.
Okay.
So this is the location of where it is available in your system. Okay. So this is a quick way to see. So here it will tell you how it is solving exactly what it is doing. Okay, then you can go over it. Okay. Yeah. So similarly, you can search for anything in the source code.
Okay. Thank you.
Yes, Sarvesh, if you want to see the residuals, then you need to add the residuals, one file named residuals in your, I think it is in your control dict, and then in your control dict file, sorry, in your system folder, you have to add the residuals file, and in your control dict, you need to add one command saying that you need to log that residuals file. I think that we have that Harish has demonstrated yesterday. Okay. Yeah. So process is similar. You can add those residuals, monitoring everything over here. You can monitor the temperature, pressure. I think tomorrow we'll again demonstrate that to you once of how to monitor the stream tracer. So all those functionalities, whatever you see, can be added into one tutorial, but then the tutorials keep getting lengthy and lengthy. So we are not showing all those things in every tutorial, but that is possible that all those functionalities can be added later on. What is the status? Has everyone finished? So yeah, this is my day 3. I will extract the cavity convection case. Inside that is my zero constant and system folder. I will copy that to my run directory. My run directory is already open. I'm copying it there. If you see cavity convection is copied, then from my terminal, I will go to cavity convection. Now here you have to run only 2 commands. One is block mesh and the other is buoyant simple form. Rest of the explanation, whatever is there, it is there in that video. Yes.
John, I have a doubt. Exactly, I am facing this problem. Previous time also I have faced that one when I am making a on-zipping the file and I'm pasting on the wrong folder.
Yeah.
Every time there's in every file there is some file is extending with a dot identifier or something. file
Yeah,
it
yeah, yeah.
is creating.
So that if you extract with WinRAR, so even now, right, I was also facing that same problem. But if you extract with this WinRAR, that's why
Okay.
when I extracted with WinRAR. So you go to click on it, extract. This default Windows extractor is creating those files. Okay.
Okay.
So see
When
now,
if it is opening it in the normal one, it is not creating. When you are putting it on the run file, it is creating the program.
okay, maybe it is creating over there, but if you extract with WinRAR, then there is no problem.
Okay.
Okay.
Thank you.
Just that. So this is my temperature, and this is my velocity field, right? So you see some sort of a circulation that is happening inside that. Now, if you want to view this, what you can do is you can add a stream tracer. Okay, you click on stream tracer, and then scroll down. Now, instead of going for a line source, you go for a seed type. No, not seed type. Is it? Yeah. Let me go to stream tracer, apply. Here. Yeah, here. So seed type, change it to point, right? And you see this sphere. When you increase the diameter of that sphere, say to something like 1, it will cover your whole geometry, and then click apply. Now here, because I've added only 100 points, I can maybe add say 1000 points, and it will become more and more dense if I increase it to say 10,000 points. So here you can see the circulation. I can hide there is an option of hide sphere, so you can see this. So this is how your flow will be moving inside. This you're visualizing. And you see that there are two separate pockets forming at the two corners. Okay. So this is it, I think, for this session.